Okay, so once we've established the procedure for calculating the outlet temperature in the reversible conditions, okay, with delta S equal to 0, we now need to calculate the reversible work. And so to do that then, we're calculating the delta H across the compressor. So we previously did the energy balance. So we're wanting to calculate delta H, and we're doing that between the outlet conditions and the inlet conditions. And so as we've discussed in the previous videos, we can separate this into the ideal gas part, and then the departure at the outlet and the departure at the inlet. And so for each of these parts then, we're going to be calculating the delta H for the ideal gas, so that's just the integral from T1 to T2, and then we're calculating the departure function at the inlet and the departure function at the outlet. And so there's a number of steps to do this, but as long as we know what T1 and T2 are, then we can calculate the reversible work. Now, in these integrations, we need to substitute in the equation of state, but then also for both the enthalpy calculations, but also for the entropy calculations, we need to calculate this. We need to have an equation for P to T, and so I'll go through that now. Okay, so to get the partial differential for the Peng-Robinson equation, we can sort of split this into two parts. So I've just written out the equation up here. Okay, and then we take the differential and we lose the t term here, and then in the second term of the equation over here is alpha t. And so when we take the differential, because all this other stuff is just a function of volume, and we're doing the differential with respect to constant volume, then we're only interested in this alpha term. So alpha is defined as this. I've just taken that from the definition of the Peng-Robinson equation, and then I'm just going to use the chain rule to calculate the differential. And so once I get the differential down here, then I simply substitute that back into here, and I've now got my P to T term that I can use in my delta S equation and also in my delta U equation. So once I have my equation for P to T, I can substitute that in and then do my integrations in MATLAB or Excel. Once I've got my reversible work, then I need to calculate my real work, and so that'll be the reversible work divided by the efficiency of the compressor. Now what we know is we know the amount of work that the compressor is doing, or equally we can say we know the delta H across the compressor, but we no longer know what the outlet temperature is. So to determine what the outlet temperature is, we can do a process similar to what we did with the entropy before, and that is that we can start by calculating. Okay, so we know what the inlet conditions are, so we solve for the inlet volume at T1 and P1. We can calculate the H departure at those inlet conditions. Then we can guess what the outlet temperature is. Then we can solve using MATLAB or Excel for the volume at 2. Okay, and then so that's at T1 and T2 and P2. So once we've done that, then we can calculate the departure function at condition 2. Then we can calculate the delta H star as the integral from T1 to T2 CP star to T. Once we've done that, then we've got all the bits we need, so we can calculate the change in enthalpy is equal to the ideal gas contribution plus H departure at the outlet minus H departure at the inlet. Then we can say, okay, is delta H equal to the real enthalpy change that we're expecting from the efficiency that we've applied to the compressor. So if yes, then we have found the outlet temp. Okay, and then if no, then we go back and we make another guess of temperature, and then we keep repeating that until we've found what we needed. Cool. Okay, thanks for your attention.